Let's start. The topic of this study is outlier detection in large datasets, and here are the authors. Introduction. So outliers are well-known problem in all experimental, scientific and industrial fields. Many techniques for detecting and identifying them have been proposed in the scientific literature. When the data set is very large, non-robust estimators may provide values if the data non-robust estimators may provide biased values if the data set is affected by outliers. The computation of robust estimators, on the other hand, is much more computationally intensive, even though this latter problem has become less relevant as computing power has exponentially increased in recent years. Still, robust methods cannot be used to analyze large data sets typically seen in process industry. The study aims to provide a robust method of outlier detection for large data sets. So we'll talk a little about the proposed outlier detection method for large data set. It is basically called clever mean, clever variance and outlier detection. The study proposes a novel, robust criterion that allows the mean and variance to be estimated while at the same time detecting possible outliers. So we will be calculating mean and variance repeatedly and during those steps we will be detecting outliers as well. So these new estimators are called clever mean and clever variance respectively. Their estimation is quite trivial. When the data is being read, we compute the sum of squares, mean and variance. Where Cm0 and Cv0 denotes the zeroth order mean and variance. It is our general mean and variance. So now, assuming y1 star as the first possible outlier and removing that value from the mean and variance results in Cm1 and Cv1. We are removing our outlier from the sum, so our mean will have one element less, and therefore our mean without the outlier will be Cm1. Similarly, our variance without outlier will be Cm2. We call Cm1 and Cv1 first order clever mean and clever variance respectively. Now, if the absolute value of Cm1 minus y1 star is greater than delta times under root of Cv1, where delta is a threshold, that is 2.5, the experiment y1 star can be considered as an outlier. So if this condition is satisfied, we removed y1, so we calculated Cm1, Cv1, and then we test this condition. If this condition is satisfied, then y1 is an outlier. Similarly, we remove y1 from the series, calculate Cm2 by subtracting y2 star, calculate Cv2 and check this condition again. If it is still satisfied, y2 star is also an outlier. The procedure goes on until yk star satisfies the condition when its removal is stimulated, whereas yk plus 1 star does not satisfy the condition, then we stop. So there are some important notes that you need to keep in mind for the process. These are notes about the process. Now yk star represents either the maximum or the minimum value after the removal of previous outlier. So while checking for a possible outlier, we check the minimum and maximum value. So we take the minimum or the maximum value and calculate CM, CV, and then check the condition with the delta. If the condition is satisfied, we mark Y star as an outlier, Y star as an outlier. So we will repeat it, the process again. After we have selected the minimum and the maximum as YK, the clever mean might maintain its value while outliers are progressively removed for two reasons. So when we have selected YK, removed it, then we have selected YK this one, and that calculated clever mean, it may so happen that the consecutive process may so give us the same mean, and it can happen because when there is a particularly large set of data, the arithmetic mean can change slightly even though an outlier is removed. So for large data, if you are removing single data, our mean may vary very little. Secondly, if two outliers that are symmetric with respect to the expected value, two outliers are symmetric about the mean and are removed, the clever mean remains unchanged. Right? It would be an error to check for outliers only by looking at the value of clever mean. So we cannot just look at the value of clever mean to determine if Y star is an outlier. The clever variance, on the other hand, has a monotonous decreasing trend as outliers are gradually removed. As we remove the outliers, clever variance keeps decreasing. If clever variance is practically unvaried or further increases when the observation is removed, then the observation is not a real outlier. If clever variance remains constant or increases, then what we have removed is not an outlier. If clever variance does not increase when the observation YK star is removed, and if YK star satisfies the relation with CMK, YK star is an outlier. So if we remove and we select an outlier, calculate these values, check for this condition, and we notice that clever mean has did not increase but satisfied the condition, this one, then we have selected an outlier. Now we will compare the technique which is studied with previously known techniques. So the traditional procedure of determining outliers consists of the following steps. Firstly, the expected value is evaluated using the arithmetic mean, calculate the mean. Then we calculate the variance. Then we standardize residuals as yi minus mean by variance. So we are basically standardizing our series of data. If a standardized residual exceeds a specific threshold, usually 2.5 or 3, the corresponding experimental point is considered suspicious. So the point for which standardized residual was 2.5, we made or greater, we doubt it as an outlier. Notice that as both the arithmetic mean and the standard deviation are non-robust estimators, they are biased even though there is only a single outlier. So even if there is just a single outlier, it may affect our standard deviation and mean. So this method has that disadvantage. Now we'll look at other robust existing methods. So robust alternative for evaluating the expected value are the median, remedian, and trimmed mean. The median of a finite list of numbers is the middle value obtained by sorting all observations from lowest to highest value. To calculate the median, we sort the numbers from lowest to highest. Now, the remedian is is usually adapted for large data sets and is basically the median of series of submedians. To calculate the median, we need a large data set and we divide it into small data sets, calculate the median for each, and then use those medians to calculate median of the median. Right? Now, the trend mean is the arithmetic mean evaluated after discarding a given part of the lowest and highest values. We discard some lower and higher, lowest and highest values, and then calculate the mean. It is more or less to the traditional mean. So we talked about the robust alternatives for mean. We will talk about robust alternatives for standard deviation. A robust alternative for estimating the standard deviation is the MAD, where MAD stands for median absolute deviations. The most important advantage of median and MAD is the robustness. Nevertheless, even they do have some shortcomings. Firstly, they require data to be stored from the smallest value. If the experimental data is so large that it is stored as an ASCII file, then that file will have to be read multiple times, making the procedure particularly time-consuming. So if you are trying to calculate the median of a large file, our program needs to read the file multiple times, and that can take time. Secondly, both estimators are less efficient if compared to arithmetic mean and the variance obtained by the mean. Now, median and MAD are less efficient than mean and variance calculated from mean. It is worth stressing that the efficiency of an estimator is based on the variance of that estimator. So efficiency is directly related to the variance. The arithmetic mean has a variance related to s square by n, that is variance by n, whereas the median to pi s square by 2n, and therefore mean is more efficient than the median. In particular, estimations obtained using the median or the MAD can be inaccurate when all the outliers are positioned on one side of the two extremities of the experimental data. So if all the outliers are present on one side, our process of determining outliers using median and MAD can fail significantly. Okay, I think that's clear. Let's go to the next slide. So the most important advantage of the most important advantage of the pre-median is that even if the data set is stored as an ASCII file, the latter only needs to read once. So with median, we had to read it multiple times, which made it time consuming. While with pre-median, we only need to read it once. How was pre-median calculated? Remember, we partition the data into small subsets and calculate the median for each subset, and then calculate the median from the medians. However, this estimate is less efficient than the median. Remember, the median was less efficient than mean, and median is even less efficient than median. So although we don't need to use file multiple times, the overall median calculation is less efficient. You have to calculate this mean of subset, then calculate mean of the mean, so we calculate the median of the subset and then calculate the medians of the median. It takes time. The trend mean estimator, on the other hand, is more efficient than the median. So trend mean estimator, it is more efficient than median. We have increased efficiency. We just train the ends and calculate the mean. So it is more efficient. And in the median, if the experiment points emitted in their evaluation are negative outliers, it will be more efficient than median and even remedian if we are training outliers. Its most significant shortcoming are the estimation requires the sorting of data as per the median. So it is more efficient, but we need to sort the data like we did for median. Therefore, we need to read the file multiple times. Also, we have to define a proper trend percentage, which is difficult as we have to clearly define how much we want to train from each side, right? So it is more efficient than median because we are just training and calculating one mean. It is can also be more efficient than remedian if what we have trained is actually an outlier, but it needs to read the file multiple times, like in case of median, so that takes time, and also we need to define a percentage of trend, and that can be difficult. It's important to remember that in trend mean evaluation, the same number of elements are trained for both the largest and the smallest errors and estimated at symmetrically on the sorted data set. Hence, if a series of outliers, all of which are either very small or very large, affects the experimental data set, an equivalent amount of good points is also trained at the other extreme, and the resulting estimation of the trend mean is less efficient than arithmetic mean obtained by obtaining real outliers only. So, while training, we symmetrically trim on both sides, and if all outliers are present only on one side of the data, we will be removing valuable information from the other side. This makes our process of calculating mean median less efficient than calculating a simple arithmetic mean. Now we will talk about advantages of clever mean and clever variance over all these methods. We learned over their disadvantages, their advantages, and now it's time for clever mean and clever variance. The main advantage of clever mean and clever variance is that even though these estimators are robust, they are also very efficient. That is, they have low variance, as they are just as efficient as traditional estimators when no outliers are included in the data set. If there is no outlier in the data set, clever mean and clever variance are equally efficient to traditional mean and variance. If there are outliers, still they are somewhat more efficient than other methods. Sorry. The clever and mean and clever variance are particularly useful when there is a large number of observations. So if we have a large data set, these can be really helpful. In fact, unlike other alternatives, it is possible to get a robust estimation of the mean and variance with a single file reading of the data while simultaneously detecting the presence of outliers. We can complete the task with a single file reading. This procedure also bypasses the need of defining an appropriate level of robustness compared to the one requested by the user training percentage to implement the training mean. So we don't really need to define the percentage we want to train on both sides. The clever mean and clever variance self-regulate their own robustness according to the data set being processed. Another benefit of the clever mean over the training mean is that former does not remove the same number of largest and smallest values. The removal only is symmetry. The mean is therefore evaluated by excluding real outliers but without sacrificing any good values. I think that was clear. Now, the conclusion present in this study. So, this study deals with the problem of outlier detection in large data sets. A novel, robust method designed to efficiently and effectively evaluate mean, variance, and outliers simultaneously is proposed in this study and compared to some of the most popular outlier detection methods. Thank you.